All right. So I hinted last time that the oxidation, the burning of fossil fuels, is a short-term process that should be a long-term process. But what do I actually mean by that? I'm sure that you scratched your head and felt a little confused. If you didn't, that's okay. But if you did, that's okay as well. We're going to demystify it right now. So now let's talk about the long-term carbon cycle. So up to this point, the carbon exchanges I've talked about are relatively fast. They happen in a matter of seconds, minutes, hours, days at most. We're talking about, in the grand scheme of things, really, really small timescales. The long-term carbon cycle, however, is very, very, very different in that the long-term carbon cycle takes millions of years. So it doesn't just take a year or 5 years or 10 years. It takes millions of years. It takes millions of years, which is one of the reasons why it's kind of a big deal. One of the reasons why it's kind of a big deal. Carbon is continuously being transported through different components of the Earth system. And this process takes millions of years. Well, there are two main legs to the long-term carbon cycle. The two main legs are the geologic leg and the organic leg. So here we go. The geologic leg are these first two components. That's the geologic leg. Chemical weathering, sedimentation, subduction, and volcanism, and then back to chemical weathering. This process takes millions of years. The other process, known as the organic leg, has to do with dead organic material being buried deep beneath the surface of the Earth over millions of years, compressing into compressed carbon, what we would refer to as fossil fuels, and then eventually through many different processes, this stuff welling its way back up to the surface of the Earth and oxidizing back into the atmosphere. Once again, this organic leg also takes millions of years. So let's talk about each of these two legs really quickly, and then I will get into where here have humans effed up the carbon cycle. So here we go. So the long-term carbon cycle. And actually, you can forget this. I forgot to remove the slide. Blooper. That's okay. So the long-term carbon cycle has those two components. The geologic leg over now, and then and then the organic leg over now. And right here, what you actually have are three reservoirs. This first reservoir up here, the atmosphere, oceans, and the biosphere. This reservoir down here are what are called carbonates. Don't worry, I'm going to tell you what those are in a second. And then this reservoir over here, buried organic carbon. All right, so let's talk about the geologic leg first. So the geologic leg starts out with granite exposed on the surface of the Earth. You can actually see granite in a lot of the rocks that are near volcanoes or that are that have been present on the surface of the Earth for a long time. And then much later, like millions of years later, natural processes actually convert that granite into carbonate, like limestone right here. And limestone, this is the kind of stuff that chalk is made out of. This is a carbonate rock. So how does this happen? Well, here's how it happens. It all starts in the atmosphere. So in the atmosphere, there is all kinds of rain. right? It rains here on Earth. I mean, at least it still does if you don't live in California. It still rains. Well, there's carbon dioxide in our atmosphere. There would be carbon dioxide in our atmosphere if we weren't even here. Well, that carbon dioxide gets absorbed into rainwater to create carbonic acid. Now, this is the kind of stuff that's going to melt you or anything like that. It's only slightly acidic, but when you have many raindrops hitting a granite rock over many years, you're going to get what's called chemical weathering. Over time, that carbonic acid is going to do its job, and it's going to, over time, dissolve silicate rock. It's going to dissolve granite. It's going to dissolve silicate-based rocks. And then those silicate-based rocks are then going to be absorbed. They're going to be dissolved into this carbonic acid water solution, which we oftentimes refer to as simply river water or stream water or lake water. Well, if this is happening on a mountainside or anywhere where gravity is moving the water from one place to another, all of that dissolved stuff moves with it. That marks the transport phase. In the transport phase, this solution of dissolved rock in our water moves its way downstream and out into the ocean. As it moves out into the ocean, all of this solution, this dissolved rock, precipitates out and sinks all the way down to the bottom of the ocean, all the way down to the ocean floor. Well, guess what? This process is a continuous, ongoing process. So right now, as we speak, in our oceans, there are actually some of this stuff precipitating out of the ocean and sinking to the bottom of the ocean. Now, at this point, one of the components of the silicate-based rock in particular is calcium. And that calcium reacts with the carbon dioxide to create what's called calcium carbonate. It's basically the stuff that antacid tablets, if you've ever eaten Tums before, it's made up of that. Many chalks or types of chalk are made up of this. Well, this stuff precipitates out, wafts its way down to the ocean floor. But while that's happening right now as we're speaking, in our mountains, there's rainfall. And rainfall is weathering those mountains and moving that down into the ocean as well. So this process is continuously happening. And so basically what's happening is over time, what you're getting is a layer of calcium carbonate sediment, then another layer on top of that, another layer on top of that, another layer on top of that, another layer on top of that. And these layers are starting to compress each other in a process called lithification. At this point, all of this stuff that's settling down to the bottom is compressing now into an actual sedimentary rock. So anyway, here's how the process goes again. Carbon dioxide dissolves in rainwater. The rainwater, which is now slightly acidic because of that carbon dioxide added to it, chemically weathers a mountainside, moves all of that stuff downstream into the ocean, where it precipitates out and sinks to the ground. And that is how our ocean floors actually come to be. So that's the first leg of the geologic, that's the first leg, or that's the first component of the geologic leg. So now you have this ocean floor that is made up of calcium carbonate. Well, we have actually changed this leg, but not in the way that you would think. The fact of the matter is, as Earth has been warming up, that has actually changed this process. Here's how. A warmer world is a wetter world. Contrary to what most Californians believe, as the Earth is heating up, it's actually going to get wetter, not drier. It's going to get wetter. And so increasing our temperature increases the amount of weathering that we experience. Increasing the amount of weathering that we experience or increasing the amount of rain increases the amount of weathering. So here's basically what happens. This is actually a negative feedback loop, and I'll tell you what that is in a second. So what actually happens is as Earth temperatures go up, more moisture is present in the atmosphere. More moisture means more rainfall. More rainfall means more carbon dioxide absorbed by that rainfall. That means more chemical weathering occurs. More chemical weathering means more of the stuff is dumped out into the bottom of our oceans. That sounds like a good thing, right? Here's the problem, though. This is a very, 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 very long-term process. This takes a really long time to happen. But what the ultimate result of this is a counteraction of Earth's warming. This can actually lower Earth's temperature by taking carbon dioxide out of the atmosphere. That is what is referred to as a negative feedback. A warmer world triggers a process that causes cooling. Now, we're not going to focus a lot on that right now, but I just wanted to do that justice right now. Okay. So now we have this ocean floor that is covered with calcium carbonate. Well, if you've ever taken any kind of earth science class, any kind of geology class, or ever experienced an earthquake, you know Earth's crust is not stable. It's not one giant solid chunk of rock. Instead, it's actually made up of many different tectonic plates. And these tectonic plates are pulling apart from each other, moving alongside each other, and ramming into each other. Well, ocean plates in particular, ocean floor in particular, is actually subject to a process called subduction. Here's basically how subduction works. That oceanic crust, which now calcium carbonate is present on, is at some point doomed to subduct. Here's basically what happens. That ocean floor is very, very dense. And at some point in its lifetime, it is going to collide with another tectonic plate. If the other tectonic plate is land, it is actually lighter. And so it actually floats to the top, and that oceanic crust actually sinks beneath the surface of the Earth in a process called subduction. Well, when this process happens, the oceanic plate and all of that calcium carbonate that's on top of it sinks down with it. Well, as you sink down in the Earth, you actually get closer and closer and closer to the Earth's core. The Earth's core is really, really hot. So as this oceanic crust is actually sinking beneath the surface of the Earth, it's getting hotter and hotter and hotter. And at some point, it gets so hot that it actually melts into liquid hot magma. And all of that carbon dioxide that was absorbed by the calcium carbonate now actually breaks off and becomes gas again. And so dissolved in this liquid hot magma is all of this carbon dioxide. Now, that being said, so now you have this pool of liquid hot magma building up, and it can't just stay there forever. It's hot, it's lighter than its surroundings, it bubbles its way up until eventually, boom, volcanic eruption. And so volcanic eruptions such as Mount Pinatubo in the 1990s, such as Mount Tambora in 1815, such as the Yellowstone caldera, those are actually all a component of the long-term carbon cycle. The carbon dioxide that is released from those explosions is actually a release of carbon dioxide that has built up over millions of years of continuous chemical weathering and subduction. So that is actually a natural process that itself doesn't increase carbon concentrations, because other natural processes, chemical weathering in particular, actually offset it. The tubo emitted a lot of carbon dioxide into our atmosphere. It ejected approximately 42 megatons. That's a lot of carbon dioxide. It ejected 17 megatons of sulfur dioxide. It ejected 3 megatons of chlorine and 491 megatons of water vapor. So really the head honcho, the big eruptor, is water vapor in this case. So just to summarize really quickly, if I were to draw it up here, basically, you start with carbon dioxide in the atmosphere. Carbon dioxide in the atmosphere. It dissolves in rain, rains down onto the ground, chemically weathers that ground, pushes it down into the ocean, where it then settles down on the ocean floor. This ocean floor eventually subducts beneath the surface of the earth, where it becomes liquid hot magma. It then bubbles its way back up, erupts out in a volcanic eruption, and the process begins again. The time it takes to do one lap of this is millions of years. Even though it seems like that volcanic eruption happens really, really quickly, that is actually just one component of a millions of years cycles. That's just one step. Just like how chemical weathering is happening right now as we speak, volcanic eruptions are happening right now as we speak. As the earth gets warmer, we're going to see a little more rain. And so this process actually may be amplified a little bit. That being said, that's not really what we've done to disturb the long-term carbon cycle. To understand what we've done to disturb the long-term carbon cycle, we have to look at the organic leg, which we're going to do in the next video.